Hello, this is an introduction for lab number 2. I hope this will help. Um, I had mentioned earlier, and if you remember, we can start a little ahead of ourselves since we have that field trip next week. So I'll give an introduction on weirs for flow measurement in case we see any of these structures in our field trip. Weirs are not the new thing. If you look at this Weir experiments, coefficients, and formula. This is from 1907. So weirs have been used for a long, long time, and there's still a few people doing research with them. So what are weirs? Weirs are overflow structures built across open channels to measure volumetric rate of water. Uh, so this is an example of a weir. And sometimes you can see those as just a structure to control flow, but it can also be used to measure, not just to control, but to measure. The crest of a measurement weir is usually perpendicular to the direction of flow. So if we have the flow in this direction, and here is the edge of the structure, then the edge of the water, this is crest, is measured perpendicular, this is the direction of flow, to the direction of flow. If this is not the case, calibrations must be made. So whenever you have this situation, there's already formulas that have been developed. If you don't have that situation, you'll have to calibrate your situation accordingly. So what is the rationale behind the weir? Well, what happens is that you have your weir here for your open channel, and you only have to measure the depth of water here prior to the channel or upstream from that channel or weir. And then if you have all the units and dimensions of that weir, you can measure the amount of flow rate. I want to point out some of the weirs that you might see sometime in your future. Buckbill weirs are usually used to provide a constant upstream depth, like in this case, and they're generally not used as flow measurement devices, but they can be calibrated as flow measurement devices. So that is important to know, that if you use them to measure flow rate, they have to be calibrated. And these oblique weirs are at an angle with respect to the center line. They're not necessarily straight from the center line. So here is the center line, and this is their oblique or at an angle, and then this one is also at an angle. Let's review a few terms that are important. Notch is the opening which water flows through. So that notch, it could be a V notch, meaning then water comes down a V, or just a square notch or rectangular notch. The crest is the edge which water flows over. So here is your crest and the depth of that crest. Nap. Nap is the overflowing sheet of water, and then the length is the width of the weir notch. Well, if it's rectangular, of course, or square. So this would be your width or your length in this case. So why do we use weirs in open channels? Well, because they're capable of accurately measuring a wide range of flows, and they're easy to construct. They're portable and adjustable, not all of them, but you can make them portable and adjustable, and if there's floating debris, it'll go over the structure. The disadvantage is that it requires a large head, and of course the upstream pool must be clean of sediment. So if you have your weir structure and here's water, what happens is that upstream you can have accumulation of dirt at the bottom, and that will affect your reading. So you need to keep it clean upstream from where you make the measurements. There's different types of weirs, and we've mentioned a few now. Weirs are identified by the shape of their opening or notch, and you can have a V notch, you see here, a sutro, which is kind of a weird shape, and a rectangular. And these are plate weirs. So in this case, you have something that's kind of portable. There's different two types of weirs. The edge of the opening can be either sharp or broad crested. So you can have either sharp, kind of like a plate, or then you can have broad crested, which is usually more permanent structure that you'll have in the channel. Weirs can also be designed as suppressed or contracted. So whenever you have contracted, it doesn't take the whole width of the channel. In the case of suppressed, it does take the whole width of the channel. And it seems kind of like backwards, because you would have thought that, this was suppressed and this was contracted or something, but it's because they call it suppressed because the lateral flow contraction is suppressed. So there's no contraction. It's suppressed. Anyway, so this is a very important notation, and you'll see why in a couple of slides. We could also use flumes for flow rate measurement, and there's two types of flumes. And flume is really an obstruction along the channel. And you can have either a Venturi flume, which is basically just like this here, just a contraction in the channel, and that causes the velocity change. The flow is the same, but here you have a wider and here is narrow, so the velocity will increase here, causing a hydraulic jump downstream, and we'll talk about the conditions for hydraulic jump. And there's also what's called a partial flume, which is a Venturi flume, but also has a steep floor. So in the case of the Venturi flume, it's kind of a straight canal, and you just change the dimension of the width. But in the partial flume, both the width and also the slope at the bottom change. These partial flumes, you'll see a lot of flow measurement in wastewater treatment plants. So there's two types of flow, the free flow or modular flow, where the nap discharges into the air, and this is preferred. We want to have this as free flow, to have an area here that's kind of open to the atmosphere. And we have the submerged flow or non-modular flow, which discharges partially underwater. We'll see an example of this in the lab. There's changes in the downstream depth that will affect the flow rate, and the transition submergence is an important concept, which is the energy, the ratio of energy from the free flow to the submerged flow, or from downstream to upstream. So that's called the transition submergence. It's an important concept. Remember, I told you that it is important to have this free flow or modular flow here going over the crest. What happens is that if you don't have this open to the atmosphere, it'll create a vacuum, and so the pressure will change and the energy will change. So this situation only happens, or it's more commonly a problem, on suppressed weirs. Remember, the suppressed weir is the one that is the whole width of the channel. So for those cases, that's when you can get this type of situation where you get reduced pressure under the nap. So in those cases, you would have to add an aeration pipe. So this is one of the equations for the flow in a rectangular weir. And what I want to point out is that this expression only applies for units of feet and second. do not apply these with meters and seconds. So K is a constant typical for that weir. L is the length. H here is the depth of the crest, and I apologize for yawning, it's very late here. And then we have a K value, which depends on the properties of the weir. We have P and H. In the case of a triangular or V-notch weir, you have an angle theta, and that's what you have here. And then the H is the crest in this case that we have here, and then the K value, which is approximately 0.585. And again, this only applies for units of feet and second. Then we have the broad crested weir, and that's sort of like a little dam that could be used to measure the flow. We have a constant, and we have the length and H, which is the H on the crest. And then we have the sluice gate, and this is what you will see in your laboratory. And here is the flow rate. And this is a difference between H and Y, and you'll have in your lab some rulers on the side, and if not, you have to do it. So this is your H value and your Y value as you open that sluice up or down or move it. And so you can have the submerged flow condition, that's the example, and calculate the flow rate. The levels, like in this case, you will have in your lab a ruler on the side of the flume that we have in the lab, but we can also measure the flow using ultrasonic level transmitters or pressure transmitters. We have both in the lab, or at least we have the ultrasonic in the lab. I hope that one day we'll be able to use it in the lab. I'll try to do that before the end of the semester. So hopefully this will help you understand a little bit of the lab and what you're measuring and why you're measuring things. And